Hello Math 14, welcome back to the next installment of Measures of Variation. This next video is pretty involved. It involves studying a topic called Chebyshev's theorem. So you may have to watch this one a time or two to really grasp the concept. That's okay. It's kind of tricky that way. There's one more video that's going to follow this one to tell you both types of Chebyshev problems. So I'm going to do one type here, and then in the next video, which is the last one for chapter 3.2, I'll do the other type of Chebyshev's problem, and that will have the homework that goes with it. Okay, we need to talk about something called the empirical rule first off. And the empirical rule is based on a distribution that's bell-shaped. So it has to be bell-shaped or normal for this to work. All right, so as you can see, I've got a histogram here that's symmetric about both sides. It's bell-shaped. The empirical rule says this. It says, look, whatever the mean is, x bar of this, if you add to the mean 1 times the standard deviation, which is whatever it is, it'll be given, and you go backwards by going the mean subtract 1 times s. So adding 1 times the standard deviation puts you to the right, and subtracting 1 times the standard deviation puts you to the left. If you go straight up, you see the green here? It encompasses this much of the graph. See, my finger traces it? The empirical rule says that's 68% of everything, whatever that distribution represents. The weights of all the tabby cats in Tehama County, whatever it is. 68% of all of them lie in this region. If you go a little farther to the right by taking the mean, whatever it is, and adding to it 2 times the standard deviation, it puts you farther to the right. Subtract it, and it puts you farther to the left. And you've got this bigger chunk of graph now between my fingers. You see that it's bigger. It's 95% of everything lies in those boundaries. This would be like an upper boundary, x max, and a lower boundary, an x min. And then finally, if you were to add 3 times the standard deviation to the mean and subtract 3 times the standard deviation, you've almost got the entire graph between my hands. That's 99.7% of everything, almost everything. There's really no reason to go beyond plus 3 and minus 3s because you've almost got it all. That's cool. That would tell you, that gives you a little bit of knowledge about that graph, how much information lies in these boundaries. But the downside is it has to be bell-shaped, and nature doesn't play that way. There's really nothing that's perfectly bell-shaped. So this is nothing more than a mathematical project that's to be done on the blackboard, the whiteboard, on paper. So what if it's not bell-shaped, like in the real world? Well, there is an alternative to that. The solution is called Chebyshev's theorem, and it's going to let us estimate percentages of data that lie between a maximum and a minimum cutoff value. But there is a catch. In order to have this kind of power, you wind up wielding a crescent wrench. If you know what a crescent wrench is, an adjustable end wrench. It's a wrench that'll do many things, but it won't do any one thing well. They're big and cumbersome. They don't fit really well on nuts. They don't work on precision equipment. You can use them for a pry bar. You can use them as a weapon. You can dig with them. But as a wrench, they don't work really well, even though they'll do a lot of things. That's Chebyshev's theorem. It does a lot of things. It just doesn't do them super well. Here's what I mean by that. Instead of saying, hey, 68% of the data lies between these two numbers, Chebyshev would say, I don't know exactly what it is, but I can tell you at least 68% lies between there. See? At least. Could be more, but it's at least 68. That's the slop that you have to put up with to have this kind of flexibility of working with a distribution that's not bell-shaped. It's still a lot better than nothing. Let's put it to play. As an example, a distribution has a mean of 20, so we're telling you what the average is, the mean, and we're telling you it has a standard deviation of 2. Use Chebyshev's theorem to find the minimum percentage of values that will fall between 10 and 30. Okay, a lot going on with that. Let me give you the tools to do this kind of problem. Let's make it methodical and recipe driven. When I'm doing a Chebyshev problem, the first thing I do is I draw a graph here in purple. I just draw a flat line. I'll put the mean down. And if they told me the maximum and the minimum values, I write those down. They'll tell you the standard deviation. I always just write that as S equals whatever the number is. And then between these two values, this minimum and maximum, I draw like a little cloud. I call it a data cloud. And it'll be some unknown percentage that I'm after. Find the minimum percentage. I don't know what it is. So I wrote question mark percentage. I do that to all the Chebyshev problems. And frankly, that's 50% of the work right there. And I didn't have to do any math. Okay, let's keep going. I wrote the steps down. Second step, I call it laying out my tools. There's only 2 tools. There's 2 equations that you need. The first equation is actually Chebyshev's theorem. It says the minimum percentage that you seek is equal to 1 minus 1 over k squared. Now, k is actually these little numbers here that are multiplying the s. Those are k values. It's the number of standard deviations above and below the mean. That's the first tool. You just write it down blindly. The second tool is x max equals x bar plus k times s. That makes sense. Look, there's some number that lies to the right of the mean. We call it x max, so that would be the 30. You get that by going the mean plus some number times s. That's what takes you to the right of the mean. It's x bar plus some number times s. All right, so after I lay my tools out, the third thing is this. You have to decide which of these 2 equations to use first. You're going to use them both, but you have to choose the correct one to use first. And here's how I choose which of the 2 to use. I use the opposite tool for what is to be found. So not to get too cosmic here, but this is what I mean by that. If I'm supposed to find the percentage, that's what I'm supposed to find. The only one of these 2 equations that talks about percentage is this one. So you'd go, well, I should be using it. But you want to use the opposite. Even though that's one you should, use the other one. So I'm going to start with x max. Now, I just transfer numbers into these positions. X max is this number that's to the right, 30. X bar is the mean, which is given as 20. It goes here. K is unknown, but S, the standard deviation, was given as 2. So I put it in there like that. Subtract 20 from 30 and you get 10, and it leaves you with this 2k. Divide both sides by 2 to get the k by itself. And you wind up with k being equal to 2. Okay? Now, you started with this equation. You have to use them both. So now it's time to use Chevyshev's theorem, the second equation. I just abbreviated min for minimum. It's equal to 1 minus 1 over k, which you found to be a 2. The squared is built into the formula. Now, I would just type this in right as you see it on the calculator and let it do the work for you. So I just type it in just like that, and you get 0.96. Since it's a percentage you're trying to find, remember the way you change a decimal to a percentage is you shift 2 places to the right and put a percent sign on it. And that would conclude finding the percentage, the minimum percentage for that problem. Okay, last video coming up, and you'll be ready to go for your homework assignment. Stay tuned.